Smith PreCalculus class, correct? And I think y'all know that he was scheduled for surgery today. I'm Mr. Hicks, and I will be filling in as long as he's not here, which may be only today, and it may be longer than that. We don't know until after everything is over with his surgery. He left me some rough notes about things he wants me to cover, and from what I have seen thus far, it should be a fairly quick review for anybody who has had college algebra. So these are principles that carry over into things that you will do in your PreCalculus class. And the first thing we're going to talk about is how you can represent solution sets to problems 3 different ways. And there are different types of problems these solution sets show up in. But when you solve certain types of equations, inequalities, and so forth, you can be told to express your answer using set notation. You can be told to write your answer using interval notation. You can be told to write the answers with a graph, or all 3 or some combination of the 3. So what we have up here are 3 different ways we can represent sets of numbers. First one we call set notation, and it's more sort of a verbal description of what the set is. So if we have something that's written like this, the way this is read is all values of x such that those values of x are greater than or equal to 4. This vertical line here is read such that, so it's all values of x such that those values of x are greater than or equal to 4. That's what we call set notation, describing the set of numbers. Now, set notation is translated into interval notation, and when you translate it, we have a couple of basic things we have to use. First of all, interval notation uses parentheses or brackets. So both the left side and the right side of your interval notation will be represented using either a parenthesis or a bracket. The bracket is used whenever we have an exact value. The parenthesis is used when we have just an approximate value. So bracket represents precision, or more specifically, a bracket is used whenever you've got the equal to included as part of an inequality. And when you have what's called a strict inequality, that means it just goes in one direction or the other. Then the other half of the interval notation is always going to be an infinity or negative infinity. Because when we say that this is greater than or equal to 4, that means it starts at 4 and it goes forever to positive infinity. So we take this and put it in interval notation. Since we start with an equal to, that means we're starting at exactly 4, so we use the bracket. So again, bracket goes along with the equal to part there. If that does have an equal to, we start at exactly 4. Has no ending point. It says greater than. It's an open-ended inequality, so that means it goes all the way to infinity. Infinity is not an exact point, so we have to close it with a parenthesis. So the parenthesis is used anytime the infinity is used. So we've translated set notation into interval notation. And then when you transfer interval notation onto a graph, it basically has the same characteristics. On the number line at the point we're starting at, which is 4, and I just like to put a reference point of 0, it doesn't have to be there. At 4, since we're starting and including the 4 with the equal to sign, the same bracket goes here that we have here. And instead of infinity symbol, we have a darkened arrowhead indicating we're going forever to the right. So we have translated from set notation to interval notation to a graph. 3 different ways to write sets of numbers. Any questions there? So if we're given interval notation then and told to interpret that, this basically says I'm going all the way down to negative infinity on the left. I'll take any values between negative infinity up to negative 3. An interval is exactly what it says. Interval represents some span. And our span goes from negative infinity all the way up to negative 3. So when we translate that to set notation, we start with all x's such that, and if we have a negative infinity, that means all of our x values are going to be less than some number. We don't use an equal to here. And what over there tells me I'm not going to put an equal to here? The parenthesis next to the 3. We said the bracket goes when you have an equal to. We have a strict inequality here. Then we don't put the the bracket we put the parenthesis, meaning it's not a equal to there, so it's less than -3, and close it with our braces. So that's all that says. From -3 to -infinity means all values of x that are smaller than -3. And then putting on the number line, again, the number line and interval notation go pretty closely together. At -3, we have the left-facing parenthesis with the arrowhead indicating we'll go forever in the negative direction down towards -infinity. So we've translated interval notation into set notation and into a graph. Questions there? Then if we're given a graph and we're told to write that in interval notation and set notation, in the graph here is very specific. We have an interval that goes from a -2 to a +3 with a bracket on both sides. So those two brackets move over here. We'll have the same two brackets here. Our starting point is -2, comma, our stopping point is a +3. So again, the graphs and the interval notation look very similar, with the significant difference being an arrowhead is replaced by an infinity symbol. Other than that, they look pretty much the same. And then writing it in set notation requires just a little bit of modification. We'll take all values of x such that, and we have a specific number on the left side of our interval and the right side of our interval, we have to put our x in the middle. So we say -2 is smaller than or equal to whatever our x's are, which will then be smaller than or equal to a +3. So the way that is read, all x's such that x is greater than or equal to -2 and x is less than or equal to 3. So whenever you have two numbers here in set notation, the x will go in the middle, your numbers on each side, and then it's just a question of whether you include the equal to part or not, and that's based upon whether you have brackets or parentheses. So those three examples represent all the different combinations of symbols that can show up when you're using set notation, interval notation, or graphing a set of answers. Specific questions there? Okay, let me put 3 up here, and you, whichever 2 I don't put, you fill in, just like we did here. So if I give you the set, you write it interval and do the graph. I give you the interval, you write it set notation and do the graph. I give you the graph, you write interval notation and set notation. While you're doing that, I'm going to find out who is here. Shows it best. Ashley Bradley.
Here.
William Flowers.
Here.
Holly Green.
Here.
Hillary Hope.
Here.
Eric Jackson.
Here.
Kelly Kamrowski Starwis.
Here.
Yolanda King. Mario Lindsay.
Here.
Tierra Mark. Scott McCrone. Ashley Melton. Thelenius Moreland. David Otwell. Kelsey Pippin. James Ray. Joshua Roberts, Nakia Smith, Jonathan Sweetberg, Tori Tisdale,
Here.
Emily Turner, Megan Wilkinson, Justin Wilson, anybody whose name I did not call. Okay, for the first one, all values of x such that those values are less than or equal to 4, just turns this around. If it's less than or equal to 4, then we've got to have our negative infinity over here on the left, comma, 4 on the right with the bracket because of the equal to. So once again, that equal to there is what tells me to use the bracket with the 4 instead of the parenthesis. Put it on the graph, again, it just turns this around. At 4, our bracket will face to the left for the less than side with the arrowhead, doesn't matter how long you extend it as long as it's obvious, arrowhead pointing towards the left. Any questions there?
There a negative sign right inside the bracket? Is that
Negative sign inside the bracket?
is that what you drew inside that bracket there?
Over here?
Up at the top?
Oh, it's just a scribble on the
Okay.
Make it dark. No negative sign up there.
Okay.
Alright, if we're going from 0 to positive infinity, then we're looking at all values of x such that those values have to be greater than 0. No equal to because there's a parenthesis there. If there were a bracket, I'd put the equal to sign and then close the braces. Any questions here? Then on the graph, on the 0, we'll put a parenthesis again because the 0 is not included. Greater than goes to the right. So the shaded arrowhead to the right. And then the interval between 5 and 8. So we start at 5, the bracket stays just like it is there. We go up to 8, close it with a parenthesis just like it is there. So we translate that into set notation, all values of x, such that x is in the middle, between 5 and 8. And since the bracket is with the 5, we'll have less than or equal to there. But a parenthesis with the 8 will put just the less than there. So that says x is greater than or equal to 5, but it's also less than 8. Or if you read from left to right, 5 is less than or equal to x, which is less than 8. So, any questions on set notation, interval notation, or doing graph? Again, those will be used as ways to represent solution sets for different types of equations and inequalities that you'll be solving. Okay, and then he asked me to review factoring. Factoring, if you've been through 3 or 4 algebra classes, is one of the most commonly covered concepts. It shows up in a whole lot of different situations. And a lot of people never get a good feel for putting the whole big factoring picture together. And it's really a fairly logical sequence you should think through when you're factoring. You get all different kinds of problems, people look at them and they just see different kinds of problems. But each problem should fit a certain pattern. But in any factoring situation, the first thing you should always do is look for a GCF, which stands for greatest common factor. GCF, greatest common factor, means I'm looking for a number and or a variable that is common or a factor of every term in your problem. And we're going to go through some examples of these in a minute. But the emphasis is on the always. Always check for a GCF. And in factoring situations, the GCF only exists about 20 to 25% of the time. But if there is a problem that has a GCF and you don't pull it out first, usually you can't go any further. It is a necessary first step to check for. Well, if you checked for it, either you pulled it out or there wasn't one, then what you do next is determined by how many terms there are in the problem. In an algebra, the word term represents those pieces of the problem separated by pluses and minuses. So if you have only 2 terms, like a 4a squared plus 5a, that's 2 terms separated by the plus, that's a binomial. If you've already pulled out the common factor, we have 2 ways that binomials can be factored. We can factor them if they're the difference of 2 squares, which is usually fairly simple to identify and take care of, or if they are sum or difference of 2 cubes. And this is generally considered the most sophisticated type of factoring here. Totally different from the difference of squares. The key thing is you do not see the word sum used with 2 squares. The sum of 2 squares can never be factored. Sum of 2 squares can never be factored. Only the difference of 2 squares. But when we move to cubes, we can factor a pair of cubes if they're either the sum or the difference of 2 cubes. Then if you have 3 terms, we call that a trinomial. There are generally 2 methods for factoring trinomials. One is known as grouping, or some people call it busting the bee. And the other is trial and error. My personal preference is trial and error, but some people like to group it and bust the bee. And then if you have 4 terms, you factor 4 terms by grouping. And in any factoring situation, one or more of these steps could apply in any factoring situation. So we'll put some examples of these up here and we will run through these.
Last semester. I gotta try to remember how to do it for a second.
So if you've never developed a logical approach to factoring, I recommend thinking through these steps. We always begin by checking for the greatest common factor. So we give in any factoring situation, I look at my numerical coefficients and I say, is there any number that divides into 7, 21, and 42? And hopefully we do know that 7 will divide into all of those. And I look at the variables to see if the same variable shows up in every term, and when it does, I find the smallest exponent. So that's just the x to the first down there. So 7x is what we call the greatest common factor of the GCF. And what we do with it then is divide each term up there by that 7x. It may help to write out that division. And down here in parentheses, we write the result we get when we divide each by 7x.
I have a question.
So here the 7's cancel. Subtract the exponents leaves an x squared. A negative divided by positive gives me a -3. Subtract the exponents leaves an x. Plus 42 divided by 7 is 6, and the x's cancel out. So your answer when you have factored a greatest common factor is easy to check by looking at two things. One, there should be nothing still common to all three terms inside. There's an x here and here, but not there. 3 and 6 can be divided by 3, but nothing over here can be divided by 3, so there's no common factor. And if I redistribute, then I should go back to what I started with, which it will. So that's what we refer to as being factored completely. Yes, ma'am.
25a squared minus 4 something.
49.
49? Okay. I thought it was AB.
Okay, so there's a GCF. Now when you're looking for a GCF in any factoring situation, 99% of the time, factoring is best done when our first term is positive. So if we have a negative first term, most people never do much work at all in factoring with first term negative. So we'd like to make the first term positive. So if I have a GCF, which I do here because 6, 12, and 15 can be divided by 3, and I have A's and B's in both terms. And if the first term is negative, I want my GCF to be negative. So I'm going to factor out a -3, which divides into 6, 12, and 15. There's an A in all three, with the smallest exponent being the first power down there. And there's a B in all three, with the smallest being the B to the first right here. So any questions about why the -3AB is my common factor? So we're going to divide each one of these by -3AB. And many of you have done so much of this, you don't need to write it out. But if you ever have any difficulty, writing it out can help you out. So a negative divided by negative gives me a +2. Subtracting the exponents leaves an A squared, and the B's cancel. Negative divided by negative is a +4. Subtract the exponents leaves an AB. And a positive divided by negative leaves me a -5. The A's cancel in that case. Subtract the exponents leaves a B squared. So by removing the GCF, the first term that's left here is positive, and then I can, of course, double check by looking for a common factor, which there is none, or distributing to see if I get what I started with. Now, after we talk about factoring trinomials, we'll come back and we'll say we have to check to see if this trinomial can be factored again. It cannot be factored again, so we're not going to worry about that right now. So once again, we have removed the common factor, and there's nothing else to be done without. So two examples of removing the GCF. Always, first step, check to see if there is a GCF. Any questions here? Then we have two terms. Again, we'll look to see if there's a GCF. There is not. If I have two terms, and it is a difference represented by the subtraction, that's what a difference is, a subtraction. And if everything up here is a square, then it's what we call the difference of two squares. If you have a difference of two squares, it will always factor into a very specific pattern. First numbers here are the numbers that I square to get 4, so that's the 2 times the 2. Got to have an x times an x to get the x squared. Second two numbers are the two numbers that I multiply times themselves to give you the 9, so that's the 3 times 3. And the key to the difference of squares is one of these has got to be positive and one has to be negative. Hopefully everybody's familiar enough with your FOIL process that we know when I multiply these out, I have 4 multiplications to do. 2x times 2x is a 4x squared. When I do the outside 2, I get a negative 6x, inside a positive 6x. 6 minus 6 cancels out. That's the reason there's no center term. Because of the opposite signs, the inner and outer products cancel. And then a positive times a negative is a negative 9. So that is the result of factoring the difference of 2 squares. Always results in two binomials, same numbers and variables, but opposite signs. Here we look for a common factor. There is none. A's here, B's there. Only factors of 25 are 5s, and factors of 49 are 7s. So both of those are perfect squares. So since it is a difference of squares, I can factor it into a 5a times a 5a to get the 25a squared. 7b times a 7b to get the 49b squared. One of them's got to be positive, one's got to be negative. Incidentally, it doesn't matter which one you put which, as long as one's positive and one's negative. That is the difference of 2 squares. Next example, again, look for common factor. There is none. It is a difference. 16 is 4 times 4. As long as I have an even exponent, it is a square. And a lot of people forget that 1 is a perfect square because 1 times 1 is still 1. So this will factor. We'll have a 4y squared times a 4y squared will give me that y to the 4th. So the exponents here must always add to give me the exponent there. We'll have a 1 times 1 to give me a 1, and one of these has got to be positive and one's got to be negative again. But in any factoring process, as long as I still have exponents left in parentheses, I have to ask myself, could I keep going? Well, this first one is the sum of 2 things that are still squares, but I can never do anything with the sum of 2 squares. So that stays like it is. But the second one happens to be another difference of 2 squares. Because a 2y times a 2y gives me the 4y squared. 1 times 1 still gives me 1, and with one of them being positive and one of them being negative, then these 2 binomials are the further factoring of that difference of squares there. So your final answer has to include the binomial that could not be broken down any further, and the 2 binomials that replaced the other difference of squares here. So that's what your final answer should look like. So again, in any factoring situation, as long as you wind up with squares in your parentheses, you have to ask yourself, could I keep going? Take a minute, try that last one. Okay, so we said in any factoring situation, you always look for a common factor first. Even numbers can always be divided by 2. And there's an a in both terms, so hopefully everybody recognizes we have a common factor of 2a. So I pull out that 2a. 18 divided by 2 is 9. Subtract the exponents, leaves an a squared. Minus 8 divided by 2 is 4. And the a's cancel out. So I remove the common factor. And then we just said if there's an exponent still in parentheses, we have to ask ourselves, can we do anything else? This is the difference of 2 squares, So that can be further factored into a 3a plus 2 times a 3a minus 2, where your final answer must include the common factor you pulled out and the completely factored form of whatever else you had there. So there's an example of putting together two of the steps, common factor and then difference of squares. If you had not pulled out the common factor, you couldn't have done anything with that. So any questions on the difference of squares? Okay, sum and difference of cubes is significantly more involved than the difference of two squares. Again, it's a matter of recognition, first of all. There is no common factor here. I have a cube there, and we got to know a little bit about our perfect cubes. There's generally only 4 you have to deal with. Our first perfect cube, which is our first non-1 whole number, 2 cubed is 2 times 2 times 2, which is 8. And then 3 cubed is 3 times 3 times 3 is 27. And then 4 cubed is 4 times 4 times 4, which is 64. And then 5 cubed is 5 times 5 times 5, which is 125. So it's good to know those first 4 perfect cubes, 8, 27, 64, and 125. Generally speaking, most of the problems you see, if they are dealing with cubes, it'll be one of those numbers. So this is the difference of two cubes. As long as my exponent is 3 or 6 or 9, any multiple of 3, that means it's a cube. And 27 is my second perfect cube. So if you have the difference of cubes, the factors follow a very specific pattern. Your first factor is a binomial. Binomial, of course, means 2 terms. And the 2 pieces that go in here are the 2 things that we cube to get my 2 terms up here. So I start with a k is what I cube to get a k cubed. 3 is what I cube to get the 27. And the sign that's up here will always be the same sign in your parentheses. So take your 2 cube roots, put the same sign between them. Now that is used to build what goes over here. Because once I write this down here, I take the first term and I square it. So k times k is k squared. And then I multiply these 2 together and change the sign. So k times 3 is 3k, but I make it positive. So that's plus 3k. And then I square the second one. 3 squared is plus 9. So I square, multiply, square. That's the pattern. Square the first one, multiply the 2 together and change the sign, square the second.
Isn't that called something? Like it's the function, I don't know. Like you have like the difference of 2 squares, but that's called something else maybe.
That's the difference of 2 cubes. I don't know of anything else.
That might be, I don't know.
Yeah.
Is it always going to break down to a binomial times a trinomial?
Every time you have a difference or sum of 2 cubes, it will always break down into a binomial times a trinomial. It is the most specific pattern of all the factoring types you've got. Always, without fail, a binomial times a trinomial. The binomial always comes directly from your cube roots of your 2 terms with the same sign. The trinomial always comes from taking those 2 numbers and square, multiply, square. Square the first one, multiply the 2 together, square the second. And the sign here will always be the opposite of the sign there. So that is the result of factoring the difference of 2 cubes. Now, fortunately, when you're dealing with cubes, the pattern is the same whether it's a sum or difference. The only thing it changes is the signs. So down here, I have 8 is a perfect cube. I've got an exponent of 3. It's a cube. 125 is a perfect cube. It is a sum. So we said it's okay to do either the sum or the difference of 2 cubes. So I start with the number I cube to get 8 is 2. Variable I cube to get a p cubed is a p. So 2p is what we call the cube root of 8p cubed. Remember, my sign in the binomial will be the same, so that's a plus. And the number I cube to get 125 is 5. So the two terms in your binomial are the cube roots of the two terms in your problem. Then the trinomial will be formed by squaring the first term. So what is 2p times 2p?
4p squared.
4p squared. So I square the whole thing, number and variable. 2p times 2p is 4p squared. Then I multiply the two together, so 2p times 5 is 10p, and change the sign, so that's a minus 10p. And then square the second one, 5 times 5 is 25. Notice since you always square the second one, it will always wind up being a positive, because it doesn't matter whether this number is a negative or positive. When you square it, it becomes a positive. So the last term is always positive. But the center term here will be the opposite of the sign here. So again, it's square, multiply, change the sign, square. Doesn't matter whether it's a difference of cubes or sum of cubes, the pattern is the same. Take out your two cube roots, put the same sign as your original problem. Square, multiply and change the sign, and square. Any questions there? Alright, try this one. Okay, I have two terms. There is no common factor, so it can only be the sum or difference of squares or the sum or difference of cubes. What did some of you first think of?
I made 4k cubed, that's what I thought of.
Okay,
2K
so you
minus
thought of it as,
4k squared.
when you said 4k cubed, did anybody else use a 4k cubed?
8.
All right, somebody used an 8, and what variable did you use with your 8?
I don't know, I just said 8.
Okay, this is actually one that we can go two ways with. We can go difference
8K.
of two squares
8k cubed.
or difference of two cubes. All right, let's see what happens here. If we go difference of two squares, because 64 is 8 times 8, right? And k to the 6 is a k cubed times k cubed, right? So if I do that, then I'll have an 8k cubed plus 1 and an 8k cubed minus 1, right? And some of you didn't start that way. Don't erase if you didn't, because there's another way to do it, okay? But if you thought of this, well, that's a square. That's 8 times 8. That's a k cubed times a k cubed, and of course 1 times 1 is still 1. You could have looked at this as the difference of squares. All right, so if you did that, that's good. But what do I have left here?
You still have a difference, so yeah, I can factor again.
I have a sum of two cubes and a difference of two cubes.
The difference
So
can be
this has to be
factored again.
factored both ways, because one is the sum of cubes now, and the other is the difference of cubes. So if I have a sum of two cubes here, I factor that into a 2k plus 1, because 2 cubed is 8, k cubed is k cubed. And then I square the first, which gives me a 4k squared. Multiply the two together and change the sign is a minus 2k. Square the second is plus 1. And then down here, since it's a difference of cubes, I do the same thing. I'll factor that into 2k minus 1 this time, because remember the sign in the binomial is the same as the sign in your difference of cubes. And then square the first, get 4k squared. Multiply the two together and change the sign, so that's plus 2k. And then square the negative 1 and get plus 1. So if you started by recognizing that as the difference of two squares, that's good, as long as you recognize that those factors were both sums and differences of cubes, which could be factored again. So you would only have gotten started if you stopped here. You are completely right only if you get to this point. Okay? Yes?
Why wouldn't it be 2k minus 1?
Which one?
Where you got it in the box right there.
This one?
Yeah.
Because if it's the sum of two cubes that I'm factoring, the first binomial has the same sign. Remember up here? Same sign in the binomial. Same sign in the binomial. So the binomial is a plus, so the binomial here is a plus.
So, I mean, I didn't do 8k to the third. I went straight from.
All right?
You know what I'm saying?
And
That's
you did
what I
it the
had.
other way.
Right.
Okay, that's what I'm fixing to do. So, since we had just talked about cubes, and since I'd written up here that 64 is one of my cubes, and since 6 is 2 used 3 times, some of you should have recognized that this is a difference of 2 cubes. So if it's a difference of 2 cubes, then I would start by using 4 is the cube root of 64, right? So I start with a 4, since 4 is cube root of 64. What's the cube root of k to the 6th? K squared. So we start with a 4k squared here. Then the sign's going to be the same. That's going to be a minus, and I've got a 1. And then I build the second one by squaring the first. So 4 squared is 16k to the 4th, so it's 16k to the 4th. Multiply the two together. Change the sign, so that's plus 4k squared, and then square the second one to get plus 1. So if you had focused in on sum or difference of cubes, this is the way you would have started. Would you stop right there?
No.
No,
No, because
that 4k squared is a difference.
you have a difference of 2 squares right here. So if I have a difference of 2 squares, that has to be broken down again. That'll be a 2k plus 1 and a 2k minus 1. And over here, can't do anything with that, so it'll stay like it is. Now those two answers look different, don't they? Based upon the sequence and the way we started. It's a unique situation. When you have something that is a difference of squares or a sum or difference of cubes, well, it actually only if it's a difference of cubes, it can be factored 2 ways. One way, if we start with the difference of squares, leads us to a trinomial that cannot be factored again unless you happen to know, which nobody in the world does except those of us who teach math and like this crazy stuff, that these two would be the factors of that right there, which is no way you can derive it from any factoring principles. So these two answers are both correct. But what we should learn from this is if we have an option of beginning with the difference of squares or the difference of cubes, the difference of squares should be done first because that leads to a more complete factoring process than starting with the difference of cubes. So again, both of them are right in terms of applying the principles of factoring, but in a sense, this is more completely factored because of being able to break that down in a very specific pattern. It breaks down into these two trinomials, but being able to do that is not within the realm of any type of factoring you've ever talked about. So again, both of them are correct. This is more correct in a sense. So an illustration of both difference of cubes and difference of squares. The difference of cubes is the one that follows the very specific pattern that basically is memorization. Take your two cube roots, put them here, and then square the first one here. Multiply the two together and change the sign here. Square the second one here. So any questions about sum or difference of cubes? Okay, so those are all possibilities when you have two terms. That's the key thing, two terms. We move to three terms. Three terms are generally called trinomials. Trinomials are factored either by grouping and busting the B and grouping, or trial and error. So we have 4 examples here. These 4 examples will illustrate the sign principles involved in factoring trinomials. But the key thing is you notice there's no coefficients in front of the first term here, because when you throw a coefficient in there, it becomes significantly more complicated. So if we have a trinomial, we always check it first to see if it has a common factor. No common factor here. So if it is a trinomial, and if it can be factored, it will always factor into a pair of parentheses. Every trinomial that can be factored will factor into a pair of parentheses. The first term in each parenthesis is what multiplies to give me that x squared, which starts with an x and an x. And then the most significant thing you can learn in factoring trinomials is what the signs tell you. Whenever the last term is positive, what does that tell me about my signs in here?
It will multiply into, the two terms will multiply into 30 and add into the...
You're not answering the
They're
question.
both
I'm
either
asking.
both negative or both positive.
That's right. When the last term is positive, the sign tells me these two must be the same. Either both positive or both negative. And how do I know which they'll be?
They'll be both
The
negative.
middle one tells me whether they'll be both positive or both negative. Okay? So the last one tells me whether they're the same or different. And the center one tells me what they are. So when that's positive, these have to be the same as that. So I know automatically I've got 2 negatives here. So then I'm looking for factors of 30 that, since they have the same sign, will add to give me 11. Well, that's going to be 5 and 6. Most everybody pretty quickly recognizes that. If you didn't, you would simply run through the factors of 30, 1 and 30, 2 and 15, 3 and 10, 5 and 6, with the ones that add to give me the 11 or the 5 and the 6. So our for process verifies it. X times x is x squared. Outside of negative 6x, inside of negative 5x gives me negative 11, and negative times a negative is a positive. So those would be the factors of that trinomial. We change it up a little bit with the next example. There is no common factor. We hope to find a pair of parentheses that we know starts with a y times y to get me a y squared. The next thing I look at is the sign of that last number. When it's positive, that tells me these two will be the same, and they'll be the same as the center. So this time they're both positive. So once again, since they're the same sign, I'm looking for 2 factors of 8, add and give me 6. 1 and 8 is 9, 2 and 4 is 6, so it's got to be a 2 and a 4. Doesn't matter which one squares since they're both positive. So y plus 2 times y plus 4, pull it out, it does verify that you that trinomial. So both of those had positive last term, which tells me my signs will be the same as the center term. Same as the center term. So when the last term is negative, then, what does that tell me about my signs? Got to be different. One's got to be positive, one's got to be negative. So I've got to have a k plus and a k minus. So now, since the signs are different, I'm looking for 2 factors of 14 that will subtract to give me 5, since they have different signs. 1 and 14, 2 and 7. 1 and 14 won't work, 2 and 7 will, but then I got to make sure I put the numbers in the right place. To get a negative, the bigger combination has to be negative, the smaller one positive. So k times k is that k squared. Get a negative 7k outside plus 2k inside. 2 minus 7 is negative 5. And a positive times a negative is negative 14. So that is the correct set of factors. So last term negative tells me my signs are different and I gotta make sure I get the right number with the right sign. Last example is similar to that. There is no common factor. So I'll start with a p times p to get the p squared. Last term negative, telling me signs are different. One's gotta be positive, one's gotta be negative. So I'm looking for two numbers that will multiply to give me 45, but since they have different signs, subtract to give me 4, and that would be 95. Which one's gotta be positive?
9.
The bigger one's gotta be positive, smaller one's gotta be negative. It's really more accurate to say the bigger combination positive, smaller combination negative. 9p minus 5p gives me 4p. So trinomials aren't too bad if there's no coefficient in front of the first term here. Since there's no coefficient in front of the first term, I just have to deal with that last number down there. But those illustrate the principles that you've got to be comfortable with when dealing with the signs in trinomials. Any questions there?
Do you do one with the coefficient in front?
So what
Just
happens when we throw a coefficient up front? Okay, it becomes a completely different situation when we put a coefficient in front of the first term. Because remember, from our FOIL process, the middle term in any trinomial comes from combining the outer and the inner multiplication from your two binomials. So, as I mentioned over there, there's two ways to do this. Some people do it by grouping, some people do it trial and error. I have done this for 40 years. I'm convinced trial and error is best for most people. So that's the only way I do it. If you choose to do it the other way, that's fine. And I can work with you individually if you have questions about it. We have people in the lab that can help. But I'm going to talk about trial and error because I think that's the best way to do it. So trial and error says I've got to anticipate a couple things. I know that if it can be factored, it's going to be 2 parentheses. And since the last term's positive, the signs will be the same as the center, so everything's going to be positive here. So that's good. That makes things a little bit better. So now, instead of only being concerned with the factors of 10, I've also got to be concerned with the factors of 6. That's 1 times 6 or 2 times 3 here. We have a 1 times 10 and a 2 times 5 here. And if you're not a very good factor, I strongly recommend doing this, writing those little numbers down. If you try to keep all this in your head, if you're not a math whiz, it becomes very confusing. And having written those factors down, the factors you should always start with when you do trial and error are the factors that are closer to each other. 2 and 3 are closer together than 1 and 6. 2 and 5 are closer together than 1 and 10. So that means I'm going to start with a 2x times a 3x as my first attempt in this trial and error technique. Now we have a 2 and a 5 down there. Does anybody know why I wouldn't even try to put a 2 here? Anybody have any idea? If I put a 2 in a parenthesis, we already have a 2. That means there'd be a common factor in here, wouldn't there? But there was no common factor up here. If you always remember to check your trinomial and there's no common factor in the trinomial, there will never be a common factor in either binomial. So I know no common factor here means no common factor in this parenthesis or this one. So that tells me the 2 can't go there, the 5's got to go there. So I'll try the 2 down here. Now with the basic hints I just gave, this problem factors itself the first time. Because 2x times 3x is 6x squared. On the outside, 2x times 2 is 4x. On the inside, 5 times 3 is 15x. Since they're both positive, 15 plus 4 gives me 19x, and 5 times 2 gives me 10. So that's a trial and error technique, but it's based upon some educated trial and error. So let me review the concepts that I mentioned there. Write down the factors of 6 and the factors of 10. And then begin with the set where the two numbers are closer to each other. because about 3/4 of the time, those are the factors that work. Far more often than not. So that's why I started with the 2x times the 3x from here, and I start working with the 2 times 5 from there. Then the question is, where do the numbers go? And because I knew there was no common factor up here, that meant I could not put the 2 in the same parenthesis with this 2. There would not be a common factor in that parenthesis. So that told me to put the 2 there, meaning the 5 had to go here. And since I already knew my signs were positive, then that problem factored itself on the first attempt. So there's an illustration of trial and error with some clues that you want to try to follow. I should have mentioned, and I didn't, we should check for common factor first, but 19 has no factors, so I knew there was not a common factor there. Alright, 5a squared minus 7a minus 6. Similar situation, I check for a common factor. There is nothing common throughout that problem there. If there's nothing common, then I can factor this only if it factors into a pair of parentheses. The only factors of 5 are 1 and a 5. With a 6, I have a 1 and a 6, or a 2 and a 3. So with a 1 and the 5, that means I'm going to start with an a times a 5a. You can write the 1 in there if you want to. Remember, there's always a 1 in front of a variable if it's not written in. So I've got to start with 1a times a 5a. My signs I know must be different. I don't know which is which. You just have to try. Make one positive, one negative. Then the factors of 6 are 1, 6, 2, and 3. We want to try the 2 and the 3 first. So if I try 2 here and a 3 here, then the only way I know if it works is by folding it out. A times 5a is 5a squared. I know that. On the outside, I get a negative 3a. On the inside, 2 times 5 is plus 10a. So 10 minus 3 gives me 7a. So that's good, except what?
Negative.
Sign's wrong. I was supposed to get a negative 7a. So if your numbers are right, but your sign's wrong, what do you need to change? Switch only the signs. Don't move any numbers around. Switch only the signs. So I'm going to make that negative, make that positive. Now it gives me a positive 3a and a negative 7a. And when I do that, excuse me, negative 10a, and when I combine that, it gives me now negative 7a, and that's the combination that works. So an a minus 2 times a 5a plus 3. There's a little trial and error when you have coefficients in front of the first term. Factoring is something that requires a good bit of time to be proficient at it, but it is something that is a part of many other things that you do. We don't know when Mr. Smith will be back. He could well be back Tuesday, but if he's not, I will be here. If I'm here, we'll continue factoring. If he's here, there's no telling what you'll do. If y'all haven't figured that out yet. But any questions on the basics of factoring all the way through factoring trinomials? Have a good weekend.